So here we are, chapter 3. So what we're going to do here is, the two things we learned since the last test is we learned about the conditional statement, which is the if-then statement. And we learned about how to use truth tables to determine whether an argument is valid or not. So I'm going to have, we're going to have a problem kind of like the second test, problem number, so if you have your second test, problem number 6. I'm going to give you two logic expressions. In this case, they're going to involve an if-then statement. So I'll give you two logic expressions. And if you look at page 108 and 109, actually just page 109, problems 81 through 90. So it's going to be very similar to that. So let's just, we probably have one of these for the homework. So what they do is they give you two logic expressions. So there's one logic expression, the other logic expression. And I've given you some tables to fill out, and you're trying to determine whether these are equivalent or not. So you do that by filling out your truth table and then comparing the final answer. And actually, I'm going to just put these on, move this one down here. I think they're both the same size, 5 by 5. So the only difference between this and problem number 6 is that this one involves an if-then statement. So they only involve P and Q, so we have just two columns to fill out all the possible combinations of P's and Q's. So remember, with two variables, two statements, we make the P column true, true, false, false, and the Q column true, false, true, false. And then we write down the logic expression. So in this case, all we have to do is just copy what's in the P and Q columns. And you may say, well, why did I have to put these down? Well, that's because it's not always as simple as this. So you always write down the P and Q columns, which are the 4 different combinations of true and falses. And then you have the if-then statement. So the if-then statement says that the only time an if-then statement is false is if the first one's true and the second one's false, which occurs right here. And all the other ones are true. And this is really just the truth table for the if-then statement. And what we're going to do is we want to look at this column and compare it with the final answer down here. So here we have the negation of P or Q. So the first two columns are still true, 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 false, false, and then true, false, true, false. Okay, that gives us all the different combinations of trues and falses with just two letters, two statements. So we do the negation of P, so instead of true, true, false, false, we change the truth values to the opposite one. And then Q, it's just exactly Q, so we just do exactly what's in the Q column. And then we have the OR statement, and the OR statement says that the only time an OR statement is false is when they're both false. So you can look down here and you'll see the second row is the only time they're both false. And therefore all the other ones, as long as we have one true, and it's true. And so you can compare this column with this column. You get true, false, true, 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 false, true, true. And since these are the same, then they're equivalent. Now, I do want to point something out. If you get something that looks like this in parentheses, or if you get something like that in parentheses, what this negation out front of the parentheses means that you do everything in here and then you take the negation of it. So if I were to have the table for this particular case, I have to have one more column to take into account the negation part. So the first two columns are P and Q, just like here. The last three columns are going to be the whatever's inside here. So let's just use this one. So this is going to be if P, then Q, and then I'm going to have the negation outside. So this negation here gives you do the opposite of the truth value for this operation. So let's just work it out just to show you exactly, because that's where most people messed up, is they didn't do the negation of the term in the parentheses. So here's our four combinations of P and Q. You have true, so this is the P column in the logic expression. This is the true Q column, so we do true, false, true, false. If it was the negation of Q, we do false, true, false, true. This is the negation of P, we do false, false, true, true. Okay, then we do the if-then statement, which we've already done this over here. The conditional operation, the if-then statement, is only false if the first is true and the second is false. Otherwise, the other combinations are true. True, true is true, false, true is true, false, false, true. Only true, false is false. When you do the negation here, you take what's in this column and you change it and put it in this column. So instead of true, false, true, true, it becomes false, true, false, false. And this would be the one that you would look at. That's your final column in this situation. Okay, so you can have something like that. Then I'm going to give you another logic expression that involves if-then statements. So, and it's also going to involve another variable. So if you had, say, P or not R and negation of Q, so that's all on the left-hand side, and then you have the if-then statement for, say, R. So how would you fill this out? Well, just like any other case, when you have three letters, P, Q, and R, you're going to have 8 rows plus 1 row for the header row. And then the number of columns, again, you don't, when you have the negation on the outside of the parentheses, this requires a column. But if the negation is right next to the letter, you can group those together. So in this case, those all go together. The parentheses are just used for grouping operations together. Because the negation is right next to the R, we're going to do that together. We have the AND statement. We have the negation of Q. We group that with the bracket. We have the if-then statement, and we have R. So we're going to need 1, 2, 3, 4, 5, 6, 7, plus 3 columns for the P, Q, and R. So I'm going to need, and you're going to need to know what I'm going to do here. I'm going to need 10 columns by 9 rows. So I'm going to go ahead and make mine 5 by 5. And I'm going to double it. I'm going to make that big enough so I can. So what you would do is you would, if I gave you 10, I'll go ahead and give you 10 rows. They'll give you 10 columns, just so you know. So, I'm going to give you one that maybe is too big in either direction or both directions. So here's something. I got to figure out what to put in these particular columns. So you're going to go P, Q, and R. Those are the 3 letters. Then you're going to write your logic expression. And in this case, I use all 10 10 rows because I've got P, Q, and R, which are 3, 4, 5, 6, 7, 8, 9, 10. Now in terms of the vertical one, I only need 8 rows in addition to this one. So 1, 2, 3, 4, 5, 6, 7, 8. I don't really need that last row, so I'll just mark through it. Okay, so now what do we do? Well, because we have 3 letters, 3 statements, and we have therefore 8 rows, we make half of the rows trues, half the rows falses for P. Then when we go to Q, we take half of that. Half of 4 is 2, so you alternate 2 trues, 2 falses, 2 trues, 2 falses. And then the final column, which is R, you alternate back and forth, just a single true, false, true, false, true, false, true, false. And you'll see that, in every column I have 4 trues and 4 falses. I just have them in these established patterns so that these are all the 8 different combinations of trues and falses that are possible with these 3 statements. Okay, now we go to these 4 columns, the ones that are either the letters or the negation of the letters. So here I just have P, so I'm going to copy exactly down what's in the P column. And then this is a negation of R, so I go over to this column and I do the negation, or I do the opposite of what's in the R column. So R column is true, false, so the negation of R is false, true. This is the negation of Q, so I'm going to do the opposite of what's in the Q column as far as the truth values is concerned. And then I have R, so that's just copying it directly. True, false. This column is true, false, true, false. Okay, now I have to do some of these operations. Well, you go to the one that's furthest inside as far as the parentheses are concerned. So we have an OR. So the OR rules are that the only time an OR is false is if they're both false. So obviously these are all true. There's a false, false. That's false. Here's another false, false. Okay, all the other ones have at least one true in them. So we can go ahead and put the trues in all the other spots. Okay, so that's this part. That's the result of P or not R. Then we're going to do an AND statement with the negation of Q. So we're going to compare this with that, the result of this thing in the parentheses with the negation of Q. And we have the AND statement. So the only time the AND statement is true is if they're both true. So we look through here. Obviously, this first one has to be true. And you see we actually have 2 cases here where we have true, true. And then we come down here and we have another case here, true, true. All the other ones only have 1 true in them. So all the other ones are false. Okay, so this is a column represents the entire left-hand side of the conditional statement that we have here. So now we're going to compare these truth values with this conditional operator. The rule for the conditional operator is that the only time the conditional operator is false is if the first one is true and the second one is false. So these are the first part, this is the second part. So we look through these, and I'm comparing this with this column. We see we have true, false here, so that's the one case where it's false. And we have another true, false down there. All the other ones either start with false. So all the ones that start with false, we know those are true. And the other one that we have here is true, true, so that's also true. And so that's the result. Okay, so that's the answer. True, 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 false, true, 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 false. Now the last thing we have is we have a logical argument to determine, using truth tables to determine whether an argument is logical or is a valid argument. So what I'm going to ask you to do is, we're going to give you a problem like one of the problems on page 119. So I'm going to pick one of those. And so let's see, which one do I want to use? I'm looking at the wrong section. That's what I want to do. Okay. So let's look at, this is problem number 9 on page 131. So a logical argument consists of some written statements, which are the premises. If we evolved a race of Isaac Newtons, does that spell right? Yep. That would be progress. Okay. Would not be progress. So that is the first premise. And we're going to make sure we first convert it to an if-then statement. It does have if, but it doesn't have then. The next premise is we have not evolved a race of Isaac Newtons. So that's the second premise. And the conclusion is that is progress. Okay, so I'm going to give you this. The next thing you need to do is you need to write down what the statements are. Or actually, we need to write these as if-then statements, if necessary. If we evolve a race of Isaac Newtons, then that would be progress. Okay, so the first one is we evolve a race of Isaac Newtons. So that's the first statement. The second one is that would be progress, or that would not be progress, doesn't matter. That would be progress, or you could do it as that would not be progress, but I'm going to use a positive, that would be progress. So those are, so if once we have those two statements, we rewrite this written argument as a argument using symbols. So the first premise, so premise number 1 is if we evolve a race of Isaac Newton, so if P, then not Q, because it says then that would not be progress. So that would be progress is Q, that negation of Q would be that would not be progress. Okay, the second one, the second premise is we have not evolved a race of Isaac Newtons. So we have evolved a race of Isaac Newtons. So the second premise is the negation of P. So those are the premise. The conclusion is that is progress. That would be progress. So the conclusion is Q. Premise, premise, conclusion. Now we write this as a full logic statements because these are the premises. If this and if that, then conclusion. So all you do is you take your two premises. So we have if P, then not Q. We connect that to the second premise with an AND, not P. And then we have to connect the premises with the conclusion with an if-then statement, a conditional statement, and then we put down Q. Again, we take the original written words, identify a P and a Q, which are the statements that make up the argument. We rewrite the written argument as a logic argument using symbols, premise, premise, conclusion. Then we make this long expression out of the two premises which are connected by an and then we have the conditional to the conclusion. Okay, and then we make up a truth table based on this logic expression. So we only need five rows because we just have P and Q. We don't have an R. So we're only going to need 5 rows. And in terms of the columns, we have two letters, so we need 2. And then if we break this up, it's very similar to the one we just did. You got that, you got that, you got that, and that. So 1, 2, 3, 4, 5, 6, 7, plus 2 is 9. So I need a 5 by 5. And again, I'm going to squish this up, make a clone, pull it over here. I'm going to make it 10 by 10. Let me move this one over, back over a little bit. Oh, didn't want to do that. Okay, so I'm going to move this just a little bit there. Put that over here. So I've got an extra column, which I don't need. So the first 2 columns are just P and Q. And then I write out my logic expression. So the parentheses just come along with the P. Then I've got my conditional, negation of Q, my AND, that's my first premise. Negation of P is my second premise. Again, I put the parentheses here. I have the if-then statement, and then I have Q, and I don't need this last column. Okay, so now we fill it out completely. So we do true, true, false, false, and true, false, because that's the 4 different combinations that we have. Then we have 1, 2, 3, 4 columns again. So where we have P or Q, we just copy down what's in the P and Q columns. So I can do that here. You don't have to do it in this order. And then you have the negation of Q and the negation of P. So the Q column is true, false, so the negation column is false, true. And P column is true, true, false, false, and the negation is false, false, true, true. Okay. Now, we do this in the parentheses first. We compare these 2 columns. We have the if-then statement. So we look to see if there's any cases where we have true and then false. We do. That's the only case this is false. All the other ones are true. True, true is true. False, false is true. False, true is true. Okay, so that's the first premise. And then we compare that with the second premise, with the AND statement. So an AND statement is true, comparing these 2 columns. The AND statement is true if they're both true. So we have 2 trues right here. We only have 1 true there, so it's false, and we have 2 false. So we get false, false, true, true. That column is the entire premise side. And then we compare that with the conclusion side, with the if-then statement. So the if-then statement result is only false if the first one is true and the second one is false. Well, these are you only have to look down and find the ones that have true to start with. This is true, true, so we're good. True, false, that's false. That's true because they're both false. So this is the result. Now what we're looking for here is we're looking for all trues. So since we don't have all trues, this is an invalid argument. Which we call a fallacy. Now, if I had gotten all trues, then I would say, since we have all trues, this is a tautology, and therefore this is a valid argument. So it's either one of the two. If there are falses in here, then it has this result. If it's all trues, then we say, just go ahead and write it out for you. So if I did that and I got all trues, what you would say is, since we have all trues, we have a tautology, therefore this is a valid argument. Okay, so it's either one or the other. So that's all we're going to do out of chapter 3. Again, what do we have? We have a question about equivalency. If the columns are the same for the end result, then they're equivalent. Then we have a logic expression that involves the conditional statement that I just give you the logic expression. And then you have to fill it out. It doesn't have to have all truths, just get the final result. And then you have to take a logical expression, convert it to symbolic logic, create the full logic statement, complete the truth table, look at the results. It's one or the other. It's either all truths or it's not. Okay, now chapter 9. I'm going to give you a question about lines. About lines, line segments, rays. And if you go to your book, and let's just give you an example to look at. What I want you to do is to be able to identify what certain lines, different types of lines are, what a line segment is. So I'm trying to find something that does this. Yeah, if you look at in the homework, 15 through 24 and 25 through 32. So what you'll see there is they ask you to find these different types of lines. So you either have to, it's more like 15 through 24. I'm going to give you a question and you have to identify what's going on here. So I will give you a line like this, a continuous line. I'll give you some points on it. Let's say it's M, N, O, P. And I would say, you know, show the line segment M, O. Okay, so what does that mean? Well, what I want you to do is to draw a picture. So you would draw a point, put the letter M, draw the letter, draw about the same length that you see in the figure, and put that. So that's your line segment MO. Let's see, I asked for show ray OM, like that. Well, array, it's important that you do it in the right direction. So what I would do is I'd put point O so that it matches up here, and I'd put point M here, and then I would draw an arrow from O to M. So I wouldn't, you know, the error people make is they say O, and they put M here, and then they draw the ray to the left, but that doesn't match up with what I have in the drawing. So you got to make sure that you do the right one. So this is wrong. This first one is correct. Likewise, if I said show line segment OM, it's actually going to look exactly like the one I had down there, because it doesn't really matter what the order is. So line segment MO is the same as line segment OM. The other thing is like a line. So if I say show line PN, what I want you to do is to, again, show where N is, exactly like on the drawing. This would be P, and then you would draw a double-headed arrow through those two. I don't want you to put all the other letters. I just want you to show the ones that apply to the one that I'm asking. And here again, it doesn't matter which. I put it in the order that's in the picture. So even though I have P first, in here I don't put P first on the line, I put N, because that's the orientation on the line. Okay, so that you can look at that. We did it for homework. There are going to be a couple of these problems where I'm going to give you one of three rules that you need to use. There's going to be something like where you have a supplemental angle situation, kind of like that. There will be one where you have a triangle. So if I draw a triangle like this, and the third case is another triangle, but you've got an external angle. So let's say there's the external angle, and then you got your triangle. Let's just do it this way. Okay. So there's your triangle. So those are the three cases. So, you know, if I gave you something like x plus 10 and 4x minus 5, in that case, let's see, I give you x plus 10 and 2x minus 5 and x there. And in this case, I give you 2x plus 20. This one's x, and this value is x plus 5. So what you need to do is you need to use the three rules. One is that if you have a straight line with an array going off of it, then that these two angles have to add up to 180 degrees. And I'm not going to work out the entire problem. You can do the math. But what we know is this angle plus this angle equals 180 degrees. They're supplementary angles. And so, you know, just like with parallel lines and transversal, either the things add up to 180 or they're equal to each other. So this is a case where they add up to 180. You solve for x, and then you plug back in. So whatever x value, you plug back in to get the angles. I'm asking for the angles, I'm not asking for x. Here you have a triangle. In this case, you'd have x plus 2x minus 5 plus x plus 10. Those are the three angles. And that's going to equal 180 because the three angles interior to a triangle add up to 180. So again, you'd solve for x, plug x back in to get the three angle values. Here we have an exterior angle and two interior opposite angles. So this is a case where you set them equal to each other. So the rule is the exterior angle is equal to the sum of the two interior angles. So it's not 180, it's equal to each other. Yeah, there's one other case I hadn't mentioned here, but if we have two parallel lines and a transversal, so here it's two parallel lines and transversal, I could also give you something like 5x plus 7, and if I were to put this as like 2x, in this case, you're either going to say they add up to 180 or they're going to be equal to each other. So again, what you do is you look at the size of the angle. This is a big angle, this is a small angle. So since this is a big angle, this is a small angle, the equation we'd come up with would be 5x plus 7 plus 2x equals 180. So then you could solve for x out of that configuration. If instead I were to say this angle is 3x plus 20, because these are both large angles, I would set them equal to each other and solve for x. So depending upon which configuration is, if they are both big angles or both small angles, then you set them equal to each other. If one is a big angle, so if I go back to our other case, if one is a big angle, one is a small angle, the rule you use is this plus this equals 180. And in all cases, you come up with the algebraic expression. You solve for x, plug back in to get your results. And there are a fair number of those kinds of problems in the test. So, you know, if I ask you to also understand complement and supplement. So if I said, what is the supplement of 80 degrees, question mark, the answer would be 100 degrees. It's the angle whose, when you add it to the original angle that you question mark, add up to 180. So angles that add up to 180 are supplements of each other. Likewise, in a complement, what is the complement of 80 degrees? Well, it's the angle which added to 80 equals 90. So in this case, to get 100, we took 180 and minus 80. That gave us, that's how we got the 100. Here we take 90 and we subtract the angle, and so you get 10 degrees. So 10 degrees is the complement of 80. 100 degrees is the supplement of 80. If I said, what is the complement of 120 degrees, you'd say, you've screwed up, because there's no angle, positive angle, that you could add to 100 that would give you 90. Okay, Pythagorean theorem. So as I said in class, all you have to do is you have to find the third unknown side. So there are two cases, really. There's the case where you're given the two legs of the right triangle, and you have to calculate the hypotenuse. So if I'm given A and B, and I need to calculate C, then you would say C squared is equal to A squared plus B squared, and then c is equal to square root of a squared plus b squared if you solve for it. So that's the case where you're given this, and you have to calculate c. The other case is if you're given c and either a or b. In that case, so in this case we know a and b. In this case we know c and a or b. So we know c, and then it's either a or b, and we have to calculate the other one. So in that case, a is going to be equal to the square root of c squared minus b squared if you know c and b. And if you know c and a, then you can just take c squared minus b squared. So that's just using the Pythagorean theorem. Similar triangles. So the main thing about similar triangles is that the ratio of the length of corresponding sides are the same. So let's just make up a similar triangle here. Let's actually make one. So if I gave you two triangles, so actually, so I'm going to do that. So, in this case, let me group all these together. Now if I clone this, and then I make it bigger, and I'm going to rotate a little bit. Okay, so I would tell you these two are similar triangles, and what you'd have to do is I'd have to tell you which angles are the similar ones. Actually, I'm not sure if I would. All I have to do is you might be able to just figure it out. Okay, but anyway, in this case, these you can see those are the corresponding angles. And so if I gave you these sides, let's say I said that was 7, and this was 5, and this was 6. Those are the lengths of the three sides. And I gave you one side over here. Let's say this was 8. And I ask you to find the lengths of the other two sides of this similar triangle. Well, what you notice is these are the corresponding sides. It's the side between this angle and that angle. So these are the ones that are the corresponding ones. So what we would say, let's call this one X, we'll call this side Y. So what we can say is that the ratio of 5 to 8, which are the corresponding sides of similar triangles, is going to be equal to, and so the numerator is the side associated with the smaller triangle. And the variable in this case is the side associated with the bigger triangle. So then you could solve for X. It's going to be equal to 56 over 5. 8 times 7 is 56. So if you cross multiply, you'll get 56 is equal to 5x. Then you divide by 5, you get 56/5. From the y perspective, again, you use the ratios of similar sides. So we can still use the same ratio of 5 to 8, this side length to that side length. So then we take, again, in the numerator we have the side that's in the same triangle. And then the denominator is going to be the corresponding side in the similar triangle. So you'll get 5y is equal to 48. So y is equal to 48 over 5. And so that's how you can use similar triangles. You just have to, you're given the three sides of this triangle, you're given one side of this triangle, and therefore you can calculate the lengths of the other two sides of the similar triangle. And the final problem is like the handout that I gave you. So it's finding the unknown angles in the figure. So you can just look at that. You have that to study with. So the third one, so it's just as complicated as homework, so make sure you know that. So a handout. known angles. I'll give you enough angles so that you'll be able to figure out all the other angles. And the rules you use are that vertical angles are equal to each other. Supplementary angles add up to 180. Complementary angles add up to 90. The sum of the internal angles of a triangle add up to 180. And the external angle is equal to the sum of the two interior angles, as well as if you have two parallel lines and a transversal, we know that either the angles add up to 180 or they're equal to each other. If they're both small angles, they're equal to each other. If they're big angles, they add up equal to each other. The small angle and the big angle add up to 180 degrees. So those are the things, the rules that we did. So anyway, that's a pretty extensive review of everything that's on the test.